In the present lecture, we will discuss the definitions and important formulas in the simple stresses and strain concept. Let's see, the first definition is strength. Strength refers to the ability of an object or material to withstand for applied force, pressure or stress without breaking, deforming or failing. Next we will see the different materials. First one is the elastic material. Elastic material which undergoes a deformation when subjected to an external loading. Such deformation disappears on the removal of the loading. Next one is the plastic material. Plastic material undergoes a continuous deformation during the period of loading, and the deformation is permanent and the material does not regain its original dimension. Next, third one is the rigid material. A rigid material does not undergo any deformation when subjected to external loading. Next we look for the elasticity. Elasticity is the property of a material which undergoes a deformation on the application of a loading such that the deformation disappears on the removal of loading. In general, every material possesses the elasticity up to the certain limit of the applied loading. That limit we are calling as the elastic limit. Next, to plasticity. A material in a plastic state is permanently deformed by the application of load and it has no tendency to recover. Plasticity is particularly useful in the operations of pressing or forging. Next one is the ductility. Ductility is the characteristic which permits a material to be drawn longitudinally to a reduced section under the action of the tensile force. In a ductile material, therefore, large deformation is possible before the failure or rupture takes place. Ductility property is utilized in wire drawing application. Next, brittleness. Brittleness implies lack of ductility. A material is said to be brittle when it cannot be drawn out by tension to smaller section. In a brittle material, failure takes place under the load without significant deformation. Examples of the brittle materials: cast iron, high carbon steel, concrete, stone, glass, ceramic material, and many common metallic alloys. Next one is the malleability. Malleability is the ability of material to be hammered or rolled into thin sheets without breaking. Malleability is utilized in many operations such as forging, hot rolling, drop stamping. Next one is the toughness. Toughness is the property which enables to absorb the energy without fracture. It shows the how much energy a material can take place before it fracture. Toughness is measured in terms of energy required per unit volume of the material to cause rupture under the action of gradually increasing tensile load. Next one is the hardness. Hardness is ability of material to resist indentation or surface abrasion. Next, strength. Strength of material enables it to resist fracture under the load. Next we look for the definition for the stress. Stress is the resistance offered by the body to the deformation. In general, we are using the notation is the sigma. So sigma equal to the intensity of force divided by the cross sectional area. In general, we are using P by A, sigma equal to P by A. And this stress is act in a direction perpendicular to the cut section. It is called as the normal stress, and this normal stress is classified into the tensile stress and compressive stress. Tensile stress means when a body stretched by a force, resulting stress we are calling as the tensile stresses. Similarly, if there is a decrease in a length of the body or compression of the body due to the force applied, that stress we are calling as the compressive stress. Next one is the shear stress. Shear stress is one which acts parallel or tangential to the surface. Next to strain. Strain is the deformation per unit length. In general, we are using the notation is epsilon or E. So epsilon equal to the deformation delta, unit length capital L. So epsilon equal to the delta by L, and units. So strain is not having the any units. So no units for the strain. And strain is subclassified into the tensile strain and the compressive strain. Tensile strain equal to the increase in length divided by original length. Compressive strain equal to the decrease in length divided by original length. Similarly, shear deformation, that is the phi. So in general, tan phi equal to the delta by L. So tan phi value is very small, so it is nearly equal to the phi equal to the delta by L. So next we have to look for the Hooke's law. Hooke's law is stated that ratio of intensity of stress to strain equal to the constant up to the proportionality limit. So intensity of stress sigma and strain epsilon equal to the constant. This constant value we are calling as the Young's modulus and denoted by the capital E. So sigma by epsilon equal to the E, and units for the Young's modulus is Newton per mm square. And we know sigma equal to the P by A and epsilon equal to the delta by L. So from this relation we can be stated that P by A divided by delta by L equal to the E, and deformation delta equal to PL by AE. Next one is the shear modulus or modulus of rigidity. It is the ratio of shear stress to shear strain, and we are denoted by C, N or G. So tau by phi equal to the G. Next we look for the stress strain diagram for the ductile materials. So here on the stress strain curve various points are there. First one is the proportionality limit. So up to the proportionality limit, stress is directly proportional to the strain, and Hooke's law is valid up to this point. Next point is the elastic limit. Up to the elastic limit, material regain its original shape and dimension after removal of the loading. Next yield point. So yield point is the phenomena where the material transform from elastic to plastic. So here two points are there for the yield point, upper yield point and the lower yield point. Upper yield point mean maximum load required to initiate the plastic deformation, and lower yield point mean minimum load to maintain the plastic deformation. Next one is the ultimate point, maximum load material withstand without any breaking. Next one is the breaking point. So breaking point is the point where the material breaks. And ductility of the materials we are represented in the terms of the percentage of elongation or percentage of reduction. So percentage of elongation is the differences between the length to the original length, which means percentage of elongation equal to the final length minus initial length divided by initial length into the 100, and percentage of reduction equal to the initial area minus final area divided by initial area. Next we look for the engineering stress and the true stress. Engineering stress is the load divided by original area of cross section, and true stress is the load divided by actual area of a cross section at any instant. Next one is the engineering strain. So epsilon equal to delta by L, and true strain equal to epsilon equal to the summation of delta by L at any instant. And here curve for the stress strain curve for the different materials, that is for the concrete, cast iron and the high carbon steel. Next we look for the stress strain diagram problem. While solving the problem related to the stress strain diagram, we have to calculate the slope of the graph, that is P by delta from the graph only. Similarly, while solving the problems on the simple stress and strain concept, if it is given the maximum stress mean, load divided by minimum area of the cross section, and similarly minimum stress is the load divided by maximum area of the cross section, and safe stress is the ultimate strength divided by factor of safety, and cross section area of the hollow part is the pi by 4 into d1 square minus d2 square. So d1 is the outer diameter and d2 is the inner diameter. And next we have to look for the principle of superposition. So principle of superposition is stated that resulting of strain will equal to the sum of the strains caused by the individual forces acting along the length of the member. So resulting deformation of the member delta equal to the summation of PL by AE. Let's see in the diagram ABCD part is given. So then the total deformation of the bar delta equal to the deformation of the AB bar plus deformation of the BC bar plus deformation of the CD bar. Similarly, you have to look for the how to solve the composite section problems. So compound bar is a structural member composed of two or more elements of different materials rigidly connected together at their ends to form parallel arrangement and subjected to axial loading, termed as the compound bar. Such a section is also known as composite section. So while solving the composite section, we have to use the two equations. One is the condition of equilibrium. So that is the total load equal to the load on the first member plus load on the second member. So P1 plus P2 equal to the capital P. Similarly, we have to consider the another one equation of compactability. That is the deformation of the one member equal to the deformation of the another member. That is the delta 1 equal to the delta 2. Let's see the few example problems on the composite section problems. Let's see the one example problem for the composite section for the concrete column. So here we have to use the two conditions, condition of equilibrium and equation of compactability. So from the condition of equilibrium, we have to say that one load on the steel rod plus load on the concrete equal to the total load. And from the equation of compactability, deformation of the steel equal to the deformation of the concrete. And one more thing here, while calculating the area of the concrete, it should be equal to the area of column minus area of the total area of the steel rod. Next we look for the one more example problem of the composite section. Here difference is area cross section of the steel and the brass, and one more difference is the length of the steel bar and the brass bars. So for the brass cross sectional area had to 2 into multiply of the single brass, and the length also different length we have to use for the equations of condition equilibrium as well as the for the compactability equation. Similarly, one more example for the composite section. So here, so outer bars and the inner bar. So inner bar having the certain gap. So that is a gap is deformation by application of load on the outer bar. So deformation of the outer bar due to the load. So that gap is deformation. So from this one I have to calculate the how much load we are applying. Then afterwards deformation. So total deformation of the outer bar is the delta, but deformation for the middle bar is the delta minus 1. As well as we have to consider the compactability equation, as well as we have to consider the condition of equilibrium equation. Next we look for the example problem on rigid bars. So here ABC rigid bar is given and it is connected with the aluminum rod BD and steel rod CE. Then applying the load on the ABC bar at the exactly midpoint between the aluminum rod and the steel rod. Then rigid bar remains the straight and aluminum rod and steel rod goes to the extensions. And these extensions are proportional to their distances from the hinged point. Otherwise, we have to use the two equations here. So here delta AL is the deformation of the aluminum rod and delta ST is the deformation of the steel rod. So that is C1 is deformation of the steel rod, B1 is the deformation of the aluminum rod. So here we have to consider the first one is the similar triangles. So AB, B1, AC, C1 are the similar triangles. So from the similar triangles we have to stated that AB by B1 equal to AC by C1. Then AB is the distance and similarly AC also distance, that is the known distances. Then AB by B1 is the deformation of the aluminum bar and similarly C1 is the deformation of the steel rod. Then 1 by delta aluminum equal to 2 by delta S. This is one equation I have to use. Another one is the equilibrium condition of the rigid bar. Then you have to consider the momentum of the forces on the rigid bar about the at the end point. So from the here you have to consider the momentums. So force into the distance. So here one is the applied force in the downward direction. Similarly, R and S are the resistance forces offered by the aluminum rod as well as the steel rod. Then so apply load, that is the 2000 into distance. So this is the downward force equal to the upward forces. R into distance from the A 1 plus S into distance up to the A point is the 2. So R plus 1 plus S plus 2, sorry S into 2 equal to 2000 into 1.5. So R plus 2S equal to 3000. So while solving these type of the rigid bars, we have to use the similar triangle equation. Another one we have to considering the momentum at the hinged point. Next is the deformation of uniformly tapering circular bar. So delta equal to 4PL by pi E D1 D2. Here D1 is the diameter at the smaller end and D2 is the diameter at the bigger end. Next, deformation of uniformly tapering rectangular bar. So delta equal to PL by A minus B TE into log of A by B. So here A is its width at the bigger end, B is the width at the smaller end. Next, elongation of a bar of a uniform section due to self weight. So delta equal to the gamma L square by 2E. So here gamma is the specific weight of the body, that is rho g. Then delta also you have to stated that rho g L square by 2E. And this delta equal to WL by 2AE, where W is the axial load equal to the weight of the body. Similarly, have to look for the elongation of the bar uniformly tapering section due to self weight, that is delta equal to gamma L square by 6E, and this is also equal to the WL by 2AE. So where W is the axial load equal to the weight of the body. Next one, elongation of the bar of uniform strength. So stress intensity is constant at any section. So for this A1 equal to the A2. Here A1 is the cross-sectional area at the support and A2 is the cross-sectional area at the end. So A1 equal to A2 into e to the power gamma L by sigma. So this can be equated that 2.3 log base 10 A1 by A2 equal to the gamma L by sigma. Next we have to look for the temperature stress in uniform bar. So uniform thermal strain, so that is epsilon T equal to the alpha into capital T. Here alpha is the coefficient of thermal expansion, capital T is the change in temperature. Next let consider a bar of length L subjected to uniform temperature increase, the bar being the free end. Then delta T, so increase in length equal to the alpha TL, and stresses are no thermal stresses. It is very important. So when bar is free to expand, there is no thermal stresses in the bar. Next similarly, so when the bar is fixed at the two ends, then stresses it will be generated. That stress sigma T equal to the E alpha T, and these stresses will be compressive when the change in temperature is positive, which means increasing, and tensile when the change in temperature is negative, which means temperature is decreasing. And one more thing, thermal stresses sigma T does not depend upon the any cross-sectional area. So next one is the which one of the support yields to by amount of small a. In the case, then total amount of expansion will be, so thermal strain minus small a. Then sigma T equal to the alpha TL minus a into E by L. So next we have to look for the thermal stresses in the composite bar. So composite bar is consisting of the two materials having the different coefficient of thermal expansion, and it is subjected to temperature, then opposite kind of stresses will be set up in the two metals. And type of stresses in the copper and steel bar. In the steel bar it will be produces the tensile stresses, and in the copper bar it will be produces the compressive stresses. It is very important. Next we look for the how to solve the temperature stresses in composite bar problems. So there you have to use the four equations. First one from the statics, tensile force in steel equal to the compressive force in aluminium, and second one is the compactability equation. So deformation of the aluminium equal to the deformation of the steel equal to the, so final deformation. And from geometry, deformation of the steel equal to the deformation from the temperature stress plus deformation from the tensile stresses. Similarly, for the aluminium, deformation, final deformation of the aluminium equal to the, so deformation due to the temperature stress minus deformation due to the compressive stresses. And one more thing you have to use, that is the delta S, you have to equate the delta A. So these are the four conditions you have to use while solving the temperature stresses in the composite bar problems. Similarly, one more type of the problem in the temperature stress in composite bar. So there is the steel bar and aluminum, is not a composite one. So steel bar as well as the aluminum bar, so both are fixed at the end and having the contacts another end. So there you have to use the three steps while solving these problems. First one is the find the free expansion or contraction due to the temperature rise or drop. So for this, free contraction in the composite bar delta equal to the delta S plus delta A. Second one is the find the expansion or contraction due to the temperature stress. So for this one I have to use the force in steel bar equal to the force in the aluminium bar. So we know force equal to the stress into cross sectional area. Then you have to use the sigma s as equal to the sigma a. So here sigma s is the stresses in the steel bar and as is the cross sectional area of the steel bar. Sigma a is the stresses in the aluminium bar. A is the cross sectional area of the aluminium bar. And third step is the free contraction due to temperature drop equal to the contraction due to the temperature stress. So these are the conditions we have to use while solving the problem related to the temperature stresses in the composite bars. Next we look for the stresses due to shrinking. While putting on the tire to the wheel, tire is heated, then it will be expand. On cooling, tire shrinks and get fitted on the wheel. So in this condition, tensile strain is developed in the tire and as well as circumferential tensile stress or hoop stress are induced in the tire. Then tensile strain induced in the tire, that is epsilon equal to the circumference of the wheel minus circumference of the tire divided by circumference of the tire. So that is tensile strain epsilon equal to the capital D minus small d divided by capital D, and hoop stress equal to the D minus D divided by capital D into the Young's modulus capital E. Similarly, while solving the problems on stresses due to shrinking, so we have to final length of the tire has to be considered, initial length of the tire plus expansion due to the temperature rise. So that is pi d equal to the pi small d plus pi d alpha capital T. So it is pi d capital D, pi d equal to the pi small d into 1 plus alpha capital T. Next we look for the elastic constants. First one you have to look for the what you mean by longitudinal strain. So longitudinal strain is any direct stress produces a strain in its own direction is called as the longitudinal strain. When an axial stress, let's consider tensile, is applied along the longitudinal axis of a bar, then length of the bar will be increased. Then this change in length per unit length of the bar is termed as the longitudinal strain or primary strain. Then the ratio of stresses to strain within the elastic limit is called as the modulus of elasticity capital E. So capital E equal to the sigma by epsilon. Then we look for the lateral strain. So strain in opposite direction we are calling as the lateral strain. Then Poisson ratio is the ratio of the lateral strain to longitudinal strain. Generally Poisson ratio is denoted by 1 by m or nu. Next we look for the volumetric strain, which is equal to the change in volume divided by original volume. We are using the notation is epsilon v. So let's see the volumetric strain due to the three mutually perpendicular stress system, which is shown in the diagram. Then delta v by v equal to the epsilon v equal to E1 plus E2 plus E3, which is equal to the 1 minus 2 by m into sigma 1 plus sigma 2 plus sigma 3 divided by capital E. Next we look for the shear modulus or modulus of rigidity. Shear modulus or modulus of rigidity is express the relationship between the shear stress and the shear strain. Then the ratio between the shear stress to shear strain we are calling as the modulus of rigidity denoted by capital G. So then capital G equal to the tau by 5. So if the given problem related to the modulus of rigidity, Especially this type of problem is given in the punching problem, to making the hole in the punching operation. There we are applying the compressive forces with the help of the punch. Then material will go to the shearing. Then compressive force equal to the shear force required for the deformation of the sheet. So then have to equate these two forces. So compressive force, that is the cross-sectional area of the punch into the stresses, how much stress we are applying, and shear force required is the circumference area of the sheet into shear stress of the material. Then have to equate these two. Then have to maybe calculate the thickness or maybe diameter of the sheet. So next we have to look for the rule of complementary shear stress. A shear stress in a given direction cannot exist without balancing the shear stress of equal intensity in a direction of right angle to it. Next we have to look for the relationship between the modulus of elasticity and modulus of rigidity, that is the relationship between the E and G. So E equal to the 2G into 1 plus 1 by M. Next one is the bulk modulus. When a body is subjected to three mutually perpendicular like stresses of equal intensity, then ratio of direct stress to the corresponding volumetric strain epsilon V is defined as the bulk modulus, denoted by capital K. So capital K equal to the sigma divided by epsilon V. So relation is E equal to the 3K into 1 minus 2 by M. So one more equation is there. So 3K minus 2G divided by 6K plus 2G equal to 1 by M. And one more thing, relationship between the E, G and K, that is E equal to the 9 kg divided by G plus 3K. And next one is the number of elastic constants for the different materials. That is, number of independent elastic constant for homogeneous and isotropic material is only 2. And number of independent elastic constants for orthotropic material is 9. And the number of independent elastic constants for anisotropic material is 21. So these are the important definitions and formulas for the simple stresses and strain concept. Thank you.